You can, anyone can say this. Okay. And what we are going to do right now is, initially, I hope you all remember the last Stellarium session that Prakash had given. And he had also shared a worksheet with you guys that we would like you to complete. And we would like you to go through it and try to solve as many questions as you can using the Stellarium tool. So today we are going to take a quick recap or a quick overview of last session. I'm not going to go into details of how to use the Stellarium application because Prakash has already covered it in the last session. What I will do, however, is I will try to give an overview of some more features of Stellarium that you can use. And you can use Stellarium as a powerful educational tool as well as a powerful astronomy tool. The reason is many a times when you know, plan your observations, or if you want to decide whether or not a certain astronomy event will be visible from your location or not, or how did any astronomy event happen in the past look like. So many a times, like one such example could be the Venus transit. So it happens every 120 years. So uh, if you have missed the last Venus transit, then you have to wait for another 100 years now. So the last one was on 6th of June in 2012. And now we have to wait for a very, very long time to see the Venus transit again. So such events like this, which are significant in terms of a date or maybe in terms of location. Let's say a solar eclipse is happening and it is happening in somewhere in North America, and it is not very easy for you to go and travel there. So then you can simply change your location and move to North America through Stellarium, and then we will actually be able to see or simulate the solar eclipse. So without any further ado, let me quickly share the screen. I hope you will be able to see the Stellarium application. So if you are connected through cell phones, I will encourage you to use a full screen mode of Zoom. And because the thing is that my screen is very big, and I'm going to be showing you a lot of things. So you can go to full screen mode on the Zoom and zoom in. So I'm also getting a couple of questions in these chat windows. So after I complete my session, which will be about 20 minutes or so, we will have a discussion. So you all can interact with us. You can tell us about the worksheet. What were you all able to do out of the worksheet? If you have any queries, you can address those. And Prakash and I will be happy to help you guys. So right now, what you see in Stellarium right is basically the landscape of IUCAA. So had you been here in IUCAA and had this conference or the summer school were offline, you would have been able to go to the central kund or the central foyer of IUCAA, and from there you would be able to see the uh, the sky or the simulation of the sky in Stellarium. So let me quickly clear two doubts. Where do we have to submit the worksheet and how do we do it? So please hold on, wait for a couple of minutes. So as soon as this session ends, Prakash will give you all the instructions very clearly, and we will be addressing all questions right up after this session. So let's begin. So this is the IUCAA campus. So anytime you come to Pune, definitely visit IUCAA. What you will see is these are four beautiful statues in IUCAA main foyer. You all know who these people are. This is Albert Einstein, of course. This is Aryabhatta. This is Galileo Galilei. And then there is Isaac Newton over here. All right. So now in Stellarium, you can change your landscapes, whichever are suitable for your activity. So apart from that, Stellarium also has a very powerful other feature called scripts. So you can write your own scripts in Stellarium using the SSC API library. So Stellarium is an open source tool. So what you can do is you can see the installation files of Stellarium and you can write your own script. For example, there exists almost like 15 or 20 scripts which come along with Stellarium by default. Now, what I have done here is I have created a script for demonstration of analemma, and I have tweaked it a little bit just to give you a flavor of how we can use the Stellarium scripting language for creating a certain demonstrations and creating certain demos using Stellarium. So now we are going to see what an analemma is, and we are going to try to simulate how does a solar analemma look all across the year. So for those who have no idea what a solar analemma actually is, so let's quickly see that first. So I think you can see my screen here now. So there's a beautiful website called analemma.com, and on that website you can learn about the solar analemma, how can you observe it across the year, and why does it occur. So let me quickly give you a brief overview. So analemma is basically the uh, you know overall figure that is traced after observing the sun throughout the year. So whenever you observe the sun every day, or let's say every 5 days, and if you keep on doing this activity over the year, you will observe that the sun's northward apparent motion and the southward apparent motion is seen. So every day if you look at the sun exactly at the same time, let's say around 11 a.m. in the morning, you will observe that the position of the sun as compared to the previous day and the next day has changed. And if you observe it over a gap of a few days, then you will see a significant change. Or even better yet, if you are observing the sun during sunrise or sunset, you will see that the reference, some landmark or some land reference where the sun is setting, that remains fixed, and the apparent position of the sun keeps on changing. Now, for doing this, you actually have to go outside. You have to be there at sunset, and you have to or be there at sunrise, and keep on observing the or marking the position of the sun. Now, in Stellarium, you don't need to do that. You can simply, search for the position of sun, and you can see how the position changes. Now, a solar analemma is a combined effect of three things. So now we all know that the Earth revolves around the sun in an elliptical orbit, right? So because of that, the sometimes the Earth travels faster around the sun, and sometimes it travels slower. So you can notice this animation over here. There are two orbits shown. So had the Earth's orbit been circular, then the orbital period of the Earth or the orbital speed of the Earth would have been fixed. So the green colored Earth that you see is kind of in a circular orbit, and as opposed to that, the blue Earth that you see in the animation here is actually the real orbit or the actual orbit of the Earth. And you can notice whenever the Earth is coming closer to the sun, it is traveling faster. And as it is going away from the sun, it is traveling slower. So that is the effect of the elliptical orbit. So sometimes the sun travels faster in sky, sometimes the sun travels slower in the sky. And that is one of the reasons. Another reason is the obliquity. So the Earth's axis is tilted. It is not exactly vertical, but it is tilted, right? So if this were the plane, then the apparent motion of the sun appears like this. So the green orbit is the sun if it were in the equatorial plane, but it is not the case. It is tilted by 23.5 degrees. So because of that tilt, you can see that the sun intersects the orbit of the apparent orbit of the sun intersects with the equator in 2 points, right? And because of these two things, because of the combined effect of these two things, what happens is you can see that the sun changes its position northward or southward, and because of moving faster or slower, it changes its position a little bit eastward or westward, and hence you can see the solar analemma. So sometimes you can see the sun a lot eastward, or sometimes it can be a lot westward. And depending upon the time of the year when you are observing the sun, you will observe the sun either closer to the north or farther from the north. So right now the sun is in its Uttarayan, and it will continue to be in its Uttarayan or its northward apparent motion all the way up to 21st of June, when there will be a summer solstice. Now, after that, the sun will start its southward apparent journey. So whenever we keep on doing observations of the sun, it is important to understand that the sun's motion is only apparent, and it is basically a combined effect of the Earth's obliquity as well as the Earth's eccentric orbit. So now let's come back to Stellarium and let's see the demonstration. So that is more the reason why you should make use of such beautiful tools like Stellarium. which give you a very good idea of how the orbits of the planets exist, how the planets really move. And so let me just quickly change the landscape. As you can see, although the IUCAA campus is very beautiful, you can see there are a lot of obstructions if you're going to do observations from the center of the Pune. So in Stellarium, you can also change the landscapes under sky and viewing options. So you can, let's say, we can go to the IUCAA Giravli Observatory, which is a 2-meter class telescope at Giravli. And this is how the sky would look from the IUCAA Giravli telescope. Now, what I'm going to do is I'm going to run a script called Analem. So this script has been tweaked a little bit to help you guys understand what a solar analemma alien is. So let's play this script. So when you run the script, it goes to the home settings. So whatever are the default settings of Stellarium. And then now you will be able to see how the sun's position changes across the year for the same time of day. Okay. So what we are doing is we are only traversing through the days or of the year or months of the year. And you can see that the sun's apparent position has changed. So sometimes whenever the sun is closer to the winter solstice, let's run the script again. Sometimes when the sun is closer to the winter solstice, you can notice that it is a lot, southward, and you can notice that the apparent position of the sun keeps on changing. So sometimes it is westward, sometimes it is eastward, sometimes it is towards the north, and sometimes it is towards the south. So on the top there is north, and on the bottom there is south. So notice the changes in the positions of the sun, and this all together put together is known as a solar analemma. Now, the solar analemma can be observed or verified visually by doing a very simple experiment. Experiment number one could be simply go and mark the position of the sun in the sky. But for doing that, you will require some sort of reference point. So nowadays, with the help of cameras, you can capture the sun with a good ND filter. So the brightness of the sun will not be too overwhelming, and some landscape in the foreground will also be captured. And if you do that, you can let me quickly show you an example. So if you do that, you will be able to do an activity like this. So notice that this person has captured the sun for all around the year, and he has not captured it every day. He has captured it once or twice every month, and you can notice the change in the position of the sun. And then after clicking many photographs, you can put together those photographs of sun's position. So what is important is you have to fix your camera angle and you don't change that. And take one good photo of the photograph and put all those images together as a composite. And I'm sure you all will be able to find out how to do all these things. So I just did a Google search for capturing a solar analemma, and this is the first result. So this is not at all difficult for you folks to find. Then there is also this beautiful simulation which will tell you how the eccentricity, if I change the eccentricity of the Earth's orbit. So notice that here, when I change the eccentricity, at the center there is the sun, and this is the orbit of the Earth, right? So when I change the eccentricity, notice what is happening to the orbit of the Earth. Right? So as it gets more and more eccentric, it becomes more and more elliptical. And see what is happening to the shape of solar analemma. So right now, let's go back. So this is the current, almost the current eccentricity of the Earth. Then you can also notice that although we say that the Earth's orbit is elliptical, it is not highly elliptical. It's very close to being circular. And in spite of that, sun sometimes travel faster and sometimes travel slower. Again, what effect does the obliquity of the Earth's axis does? So here you can see this slider over here. If I change this, you can notice that the planet's obliquity is changing, right? Right now the planet is almost horizontal, kind of like Uranus. But if you put it back to 23.5 degrees, so that is creating this figure of 8 loop. So the obliquity of the planet changes the orientation as well as the size of the loops. And then this is the axe angle. So the depending upon the change in the axe angle, the orientation of the solar analemma is going to change. So these are the three sliders. Uh, the combined effect of these three things is what causes the solar analemma, and that is something very easy to observe. Like I said, the first set of observations that you could have done would be to capture the photograph of the sun after once every month, and then put together those photos, and you will notice that the change of the positions of the sun will be very much apparent and very much clear. Another method could be not observing the sun directly, but observing it indirectly. So you can, put a very perfectly vertical pole. Maybe use a flagpole in your colleges or schools. And what you can do is you can mark the position of the tip of the shadow of the flagpole every maybe once every month or twice or thrice every month, and then you can mark the shape of the shadow that has been traced. It will exactly be like a solar analemma, because that's how the position of the sun would have changed. So you can either directly observe sun or indirectly observe sun. Nevertheless, you will be able to figure, or you will be able to capture the solar analemma. Now this is a very very simple experiment which anybody can do. What this experiment tells you is the smaller, the farthest point of the smaller loop is the solar summer solstice. The farthest point of the larger loop is the winter solstice, and the orientation or the angle gives you the uh, apse angle or the obliquity, and you can learn about these three very important features of the Earth simply by plotting a solar analemma, and you can directly measure the angles. So this is a very very simple and a beautiful activity. And to avoid actually taking observations throughout the year, you can use tools like Stellarium for understanding more about this. So this was one such activity that I wanted to show you. Let's come back to Stellarium. I will take only 3 or 4 more minutes, and I will tell you how you can understand more about different motions of the Earth. So you all probably already know that Earth has two main motions, which is rotation and revolution, right? But apart from that, Earth has three more motions that you rarely hear about. So one of the motions is called as a precession motion, where the axis of the Earth is wobbling, right? So it is revolving around itself. Now, imagine the Earth to be like a large spinning top. So you all must have seen whenever a spinning top is slowing down, it kind of wobbles like this. So if this were my spinning top, if this were my axis of the spinning top, then as the top starts to slow down, the axis starts to wobble, and eventually the top falls off. Right. So something like that is happening to the Earth, and because of that, the axis of the Earth is making a big round circle called as the precessional circle. We also call this terminology as precession of equinoxes, and that is something that we have experienced over a couple of hundreds of thousands of years. So when people were building pyramids a couple of thousands of years ago, the pole star that they had at the time was not the Polaris, but it was a star named Thuban. Currently, our pole star is known as Polaris. Right. So let's quickly, with the help of the equatorial grid, now what I will do is I will change the landscape. Change the landscape to Geneva, which is almost a let's make it. Okay. So this is my current landscape over here. Now I can also switch on the cardinal points, which are the north, south, east, west points. Now towards the north, you can see that this is the north celestial pole. Now I'm going to switch atmosphere off, so I will be able to see stars all year around. So now you can see this star, which is very close to the North Celestial Pole. What star is this? This star is the Polaris, or the current pole star. Now I'm going to switch over to the date and time window. And now what I want you to see is, let me also switch the constellation labels and lines. Now, notice that I have switched on these constellation lights. This is the pole star or Polaris. I have brought it to the center. Now, I'm going to traverse through the dates. So, it is 2022. I'm going to skip over the years. Now, I want you to mark what is happening to the position of this Polaris. So, the north celestial pole is the actual north celestial the imaginary point in the sky towards which the Earth's axis is pointing. Now, notice that it is not exactly passing through the pole star. So, this is the first many a times it is a misinterpretation that people believe that the pole star is exactly lying on the axis of the Earth. But that is not the case. It is slightly away from that. And how far away it is, you can use the different angle measurement tools which are given in the Stellarium. So there is this window called the measurement window, and then there are so many more tools that you can use. So let me just quickly. Just a second. Now in Stellarium, there are also some more tools that you can use. You can plot the ephemeris of the stars. You can get a list of all the transits as well as different phenomena that are going to happen. So you can select the objects, like let's say Earth and maybe the Sun, and you can find out which are the different phenomena. So let's say select different objects like Moon and bright stars and calculate phenomena. So these are the different occultations which are going to happen in case of the Moon. So this is a very powerful tool. Now in Stellarium, you can switch over the dates very fast. So right now you can see that the position of the pole star is moving relative to the north celestial pole. Right now, this has been only a matter of 1,000 years. Not even 1,000 years, only 100 years. Right? Now let's see what happens when we go into the year 12,000. Right now we were in the 2000 year, so it's 2022. Let's see what happens when we go to the year 40,000, maybe 12,000 years later from now. Notice this star over here. So this is a very bright star in the constellation of Lyra called Vega. Now this star is going to be a pole star of the Earth in 14,000 AD. Now you can also go back in time. So let's come back to 2022. The current pole star is the Polaris, right? Now if I go back 4,000 years ago, so if I add a minus sign here, so it is minus 2022. Right? So you can see this star over here, this one. This is close to the north. This is a bright enough star which is close to the north celestial pole. So if I keep going back into the past, let's say I go back to this star over here. So this particular star is Tuban. So this is around the time when the pyramids were being built on the earth. And at the time, the people who were alive then would refer to Tuban as the pole star. And ever since these many years, the precession of the Earth's axis has caused the north celestial pole to shift. And because of that, we can observe that the Earth's precessional circle is guiding the Earth's axis. So you can also see the precision circle in the markings. So if I zoom out now, let me quickly just switch on the markings. Notice here, you can see the precessional circle of the Earth. So this is the imaginary circle that the Earth's axis traces over a matter of 28,500 years. So it takes around 28,000 years for Earth to complete one full revolution or one full rotation of the precessional circle. And as you can see here, if I come back to the current date and time, the Polaris is closest to the North Celestial Pole. Now, over a matter of a couple of thousand years, 12,000 years from now on, the star Vega will be the pole star. So this is Deneb, this is Vega. So close to 12,000 AD, the star Vega will be our pole star, and so on. So you can also understand different types of motions of the Earth, and you can verify them using tools like Stellarium. So what we learned today was how can we understand about the solar analemma, how can we put it together in the form of a script. So in order to write a script, you will be you will need a simple text editor. So this is the script for showing you the solar analemma animation that I just covered. So it's very simple actually. It makes use of simple Java-like functions, and then all the APIs that you need to call are given in the API library of Stellarium. So if you want to learn more about this, you can go to the stellarium.org website and you will find the list of all the functions that you can use. And you just have to call one function after another in a proper sequence, and then you can create an animation or you can run your script to create an animation inside Stellarium. So that is how you can make your own script. So this is how the script looks like, and then you have to put that script in a folder where the Stellarium is installed. So in case of Windows, it is available on program files. So let me quickly show. So in Windows, if you go to the C drive in program files, there is the Stellarium installation. If you're on Linux, it is in /home/usr/Stellarium. I think it's the same path in case of Mac as well. So what you need is you need to find out this scripts folder inside the Stellarium, and then you will find the existing scripts that are there. And you can add your own script, edit it, and run it using the configuration window in Stellarium. So that's what I wanted to quickly show. Let me just come back to Stellarium now. Now, we had given you a list of questionnaire or an activity sheet that we wanted you to solve. And we wanted you to use Stellarium as the tool for that. So now I will like to invite Prakash over, and we can try to discuss about the worksheet that was given to you. And let's also talk and discuss the question and answers if there are any. So I can see that there is one hand that is being raised. So you can feel free to unmute and ask your question. If not, you can type your question in the chat window.
Thanks, Atharva. That was very interesting and detailed. Okay, now first, if you have any questions regarding the demonstrations that Atharva did, you could start with that. And then we can move on to other questions from the worksheet. Bhagwan, you had a question? You should be able to unmute yourself. Or if anyone else has a question too, please unmute yourself and ask.
If you don't have access to a microphone or anything, you can type out your questions.
Yeah, you can address it to everyone so that they can also see what question you ask. Assume it's enabled that you can type to everyone.
So,
yes.
So when I was going through the worksheet, I came across this question that we had to record the sunrise, sunset, moonrise, moonset for one day. So when I started doing that, upon rewinding and for the same day, I was getting different times. When I when I went back in time and I came back, my time was changing for sunrise and sunset.
By how much?
By a couple of minutes.
Are you for the same day, you say?
For the same day, yes.
It is likely that the sun and the moon are like a disk, and you may not be exactly getting the center of it, and it's only a little bit of error due to that.
No, but so was the time being shown by the information panel on the left. That I thought should be fixed.
Oh, it shows the sunrise and sunset,
Yes,
or
sir.
moonrise and sunset. It should be the same. I don't see a reason why it should change at all, as long as you haven't changed your location.
So if you are trying to move ahead the time forward and reverse, make sure that you pause the time. What happens is in Stellarium, whenever you change the timing, the clock keeps on going on. So in case you are trying to mark the timings, you make sure that there is a pause button in the Stellarium. You pause that. So I can quickly show you.
Sir, actually, the time I'm talking about is the one displayed on the information panel.
The one displayed on the information. Oh, you mean the
Yes, sir.
moving over here?
Yes, sir.
Oh, I see. So that is actually the incremental counter. So right now, as you can notice that the time is going on, right? So if you don't want this time to move, what you can do is you can pause this. So now this timing is no longer moved, right? So you can notice this bottom pane over here where you can switch on the constellation lines labels. There is also a button of pause, play, rewind, and forward. So if you click on the play button once more, the timing will be paused. And then you can mark all these timings, and also the timings in the information window will not change. So if you are marking or noting down any timings, it is important that you pause the slider over here and then only mark the timings. Do we have any more questions?
Yeah, does that help? I mean, I tried to do it right now. For me, the rise, set, and transit, the times remain the same. I don't see them changing. Yeah, it shouldn't. But in any case, you can get the approximate times by actually looking at the time when it transits, and as Atharva said, pause it so that you can get the exact value, as close to the exact value as possible.
Okay, sir. And sir, I also wanted to know the significance of using the equator J2000.
Yeah, that is because just as Atharva was actually explaining about the motion of the equinoxes, what happens is since the pole axis itself moves in the sky, you can imagine that the equator, the line that let's say the celestial equator that is obtained by extending the Earth's equator onto the sky, the relative position of that is also going to change. Its inclination with respect to the ecliptic. Okay, the inclination stays the same, but the position with respect to the stars is again going to change. Now, what happens is over time, when you're trying to define the zero for your right ascension, we usually take that to be the ascending node, which is, how the equator, the celestial equator, and the ecliptic line, it crosses the 2 points. And at one point, the sun, as it goes through the year, it will try to ascend, that is, go to positive declinations. And in the other one, it will set or descend, which is go to negative declinations. So we mark the point at which it starts its ascension to positive declinations as the ascending node. And this is the point that is defined as right ascension 0. Now, this is again going to change because of this equinox. Its position with respect to the constellations of the stars are going to change. Now, that is why we have to define it. If we want to be very precise, first of all, we need to define a possible reference point for this position of this point, the ascending node, and then use it for, let's say, a few decades. Till that time, the position has changed significantly. Then we redefine it and then take that to be the reference and use it for a few decades. Because you can imagine that if you don't do that, if you don't define a reference as to which year that corresponds to, every year there's going to be a very minor change. It may not matter for amateur astronomy, but when it comes to doing professional astronomy, you need to be more precise in terms of RA and TEC. And you cannot, you can, in principle, you can, make an observation today and try to decide, find the RA and TEC of a particular object you're interested in with respect to where the ascending node is for this year or currently, and you'll see that this value will be very different compared to if you had defined this position according to where the ascending node was in J2000. So this becomes a problem when you want to communicate this information to others. You can always include, the position and then give a J2022. But then somebody has to make this reverse calculation and try to figure out if they want to make an observation, if they had some archival observation or they want to make observation in the future, they'll have to work it out where exactly that would correspond to for their observation. So to maintain that uniformity, we, astronomers tend to define a particular epoch, let's say with reference to J1000, I think the 1st of January, if I'm not wrong. And then the positions are defined according to that. Before this, there was the J or B 1950, I think. So that's the main reason. Is that clear?
Thank you, sir.
Prakash, many people are messaging about where do they have to submit these?
Oh, right. You don't have to submit anything. It's just for your learning. However, only for participants of the refresher course, you'll have some questions that will, in your assessment, that will come from this worksheet. For the summer school, as far as I know, there are no assessments. So it's just out of your interest, you can complete it. And for refresher course, you don't have to submit anything, but there will be questions for it. So if you finish all this, you'll be at a better position to answer those. Gopal, you have a question?
Sir, actually, I'm asking that since our North Pole is changing with time, so how significantly it's affect our equatorial coordinate system?
How what?
How it is affecting our equatorial coordinate system? RA and deck.
Right. But if you see how we defined RA and deck, we define the 90 degrees declination to be the point of the of our celestial pole point, not the position of a star, but where the point about which our Earth seems to rotate, or the sky. If you are looking at the sky will apparently move about a particular point, and that's what we define as the north celestial pole point in the northern hemisphere. Now, this point will change depending on which point on the circle of equinox it is. It may be pointing to totally different stars. The stars are essentially constant for the time scales, most of the time scales we are interested in. But it's the motion of the Earth. And since the coordinate system is defined according to our equator and our poles, you can imagine that any motion than the regular rotation revolution of the Earth is going to change the coordinate system itself, because we are moving the coordinate along with the motion of the Earth. So yeah, go on.
What are the ways to correct the coordinate system with time? And how astronomers correct the RA and deck of any particular astronomical object with time?
Right.
Since it is changing.
So that is what they will assume. Anyway, these coordinate systems are imaginary. We just try to draw it on the sky. They don't exactly exist. So what they do is they agree upon a particular date and time, which in the latest one is 1st of January 2000. And they say that whatever was the coordinate system at that point, we will always measure it with respect to that coordinate system, even if the position of the pole has moved very minutely. But for astronomy, even that minute change is important. So instead of trying to find the position of a particular object with respect to the coordinate system that you can define now, they take it on that particular day. Everybody agrees that they will report the positions according to the coordinate system that we had on that day. And that is what we'll use for, let's say, next another 50 or another now 30 years, and then we'll change it. Or if there's something else that comes up or we decide to change it in between, then I think most likely the International Astronomical Union or some governing body like that will take that decision and people will follow. So we don't have to, if we want to exactly know the position, then we need to correct for it. So if in Stellarium, in fact, if you notice, if you have all the details on, it will give you the RA and deck for J2000, and just below that it will say RA deck on date. So you'll notice that it gives two different positions in the equatorial coordinate system itself. So the on date is the one that is on today, for today's position of the North Celestial Pole Point and the coordinate system, which is moving with the Earth. What is the location? And you'll see that the discrepancy increases as far from 2000 you keep going in time. So if you go back to 2000, it should be very close.
So just to add a little bit, the coordinate systems don't really change. The coordinate systems are kind of like a graph paper system. The origin of the graph paper changes somewhat, like the 90-degree declination is always calibrated to the North Celestial Pole. So wherever the axis of the Earth is, that is where the 90-degree declination is going to be. Also, the zero RA point used to be called as the first point of Aries. But now, the first point of Aries, or the vernal equinox, is no longer in the Aries constellation, but in the Pisces constellation. And that is a result of the precession of the Earth. So this point, where the equator of the Earth, basically coincides with the ecliptic, is called as the vernal equinox. So that point marks as the beginning of the right ascension readings. So that itself keeps on changing, and the entire coordinate system keeps on moving, and not the particular reference point. So the coordinates adjust for themselves. So as Prakash mentioned, the epoch that you choose will decide what the coordinates will be. So if you choose as the epoch as 2000, then the J2000 coordinate systems will apply. If you take the epoch of the current date, then the equatorial coordinates will change accordingly. So it is important to mark the epoch of when the coordinates were calculated and what was the reference point.
So I assume in the sky and viewing options, there's option to choose whether the equatorial coordinates that we see, no, not the coordinates, but the grid that we see is going to be the current one or the J2000.
Yes, yes.
So that is something you can choose.
So in these markings, you can choose which equatorial grid would you like. Would you like it for off date or of the 2000 date?
Right.
So that you can accordingly choose. So if I turn both of them on and I change their colors, you can see that the purple colored grid is off date and the red colored grid is of 2000. So that is how much the equatorial coordinate system has changed over 22 years, right? So that is something that you can very easily understand using Stellarium, and you can also tell how much will the coordinate system change. So instead of J2000 in Stellarium, you can change the value of 2000 to, let's say, 1900, and then you can change the epoch and accordingly have the grids added to it. That is something very powerful tool that you have on your hands.
Thank you.
Sure.
Bhagwan, do you have a question? Your hand has been raised for quite a long time.
No, sir.
Okay.
Okay, you can put your hand down. So is Vipin Das around? He had raised some question in that spreadsheet. So, okay, I'll share the screen and share. Okay, one of the question, I can't see whether he's, yeah, I can see that he's here. So one of the question he asked is how to find out, how long a particular object takes to traverse a particular constellation. So what you could do is, so there is an option to turn on, in sky and viewing options, under star lore, you can turn on this option of showing boundaries for constellations. The simplest thing would be to do it. It's pretty arbitrary. There's no, I mean, there's no real, it's not really of professional astronomical use, but let's say you just want to do it uh, for fun, want to keep track of, how a particular solar system object traverses through the sky across constellations. You can do it approximately. These grid lines, I mean, they're not based on some particular science. It's pretty approximate as far as I know. So you can, for the purposes of the activity, you can see when a particular object of interest enters the boundaries of these and then exits the boundary of that constellation, and you can mark that down. Okay, the other question he had is, I think the other question was how, okay, there was a question about uh, the timescales at which some motions are apparent. This one, as far as I remember, was for the Barnard star. This is one of the stars which has the highest proper motion, that is the transverse motion across on the sky. Again, we are looking for just order of magnitude value. So you can try to see, you can select this particular star, Barnard star, by doing a control F and searching for it, and then center on it and increase the time in orders of a year at a time, or 10 years at a time, 100 years at a time, and try to see with respect to the background stars when you're able to see it change position with respect to that, with respect to the background. And then that approximately is what I want for apparent motion of that particular star. Okay. Okay, there's a question about how we can verify our answers. I think the best way would be to actually bring it up in, uh, especially the ones that you're not entirely sure of, bring it in Slack so that other people can comment and you'll know. That is the better way. If you don't understand why something is the way it is, or you get it wrong, you can have a discussion about it too. I think it would be quite useful for both the person learning and the person explaining. You can do that in the forums on Moodle as well for the refresh course participants. I think that will be the best. These questions are not super hard, none of them. So I right now do not see the value of just providing the direct answers. And some of them are customized in the sense that I ask you to go on a particular, location, or choose a day that is customized to you, your birth date, or some location that is wherever you're living. So as long as you understand the concept, you can discuss that. The exact answers will be obvious to you once you understand the concept. And that you can discuss that on Slack. So this question by Bharati Patil on whether we can take small projects on this. So we have been discussing, Atharva and I have been discussing about this. And in the future, possibly just within a month or so, we'll probably conduct one where we'll have more experiments, actual experiments that you can do, or in the sense that you can simulate using Stellarium. Actual experiments in the sense historical experiments that people did to find, let's say, the speed of light or things to do with eclipses. We are coming with a small set of experiments that we can do and simulate in Stellarium. So we'll advertise that, and then you can join. The images we see in the in Stellarium or composite objects can be used this tool for multi-wavelength observations. There is a better tool for that. I mean, these are, in many cases, those are composite images, and but of course they show only the optical image, and that too not in different bands. It usually will have one composite image which uses information at various wavelengths and combined according to what data was available. So it won't be useful for multi-wavelength observations, but there is a tool online where you can easily do that. They have sky maps for pretty much all the big surveys and all wavelengths.
It is called Worldwide Telescope. So
is that Worldwide Telescope?
Okay. Yes. So it's a wonderful tool actually, and they have this international competition that they have just announced. So if you would like, let me quickly show you the website. Just a second.
So is this the one which also has X-ray and gamma ray sky, everything?
Yes, they do.
Okay, because there's another one. I think it's linked to Aladdin or Sinbad.
Sinbad.
Right. Okay. Those ones also have it. I don't know whether Worldwide Telescope has access to.
They do. So the
Oh,
Worldwide
it's
Telescope.
pretty equivalent, is it?
Let me just quickly share the screen.
Sure.
Yeah. So if you see this, this is called as the Worldwide Telescope. It initially was developed by Microsoft. Now it is free and open source. So anybody can use it even from a browser. You don't need to install it. You can see here they have a beautiful collection of all-sky survey, HIPS surveys. Spitzer studies are basically infrared surveys. Chandra studies are X-ray surveys. And then there are Hubble studies, which show beautiful images of the Hubble Space Telescope. And you can also create different tools using this, software. And you can simply design tools the way you would design a PowerPoint presentation or maybe a Google slide presentation. So it is that intuitive and that simple. And you just have to put together a timeline, create multiple frames, and the camera will automatically shift from one frame to another. So this is one of the tools that has already started for the journey from Orion Nebula. You can see the images of Orion Nebula, and then it is zooming out to show you the entire constellation. You can also get access to different wavelength images. You can change the imagery. You can see a drop down window over here. So this is the colored digital sky survey. You can change the wavelength to hydrogen alpha map. So this is how the region would look in H alpha. If you would like to see the radio images, they also have those. Let's say if you would like to see the ultraviolet images, this is how the sky would look in ultraviolet. It may take a while to render if you're viewing it online, but if you download the software and run it on your computer, then it will be a lot faster. So there are these so many different surveys that you can see. And so let's say Fermi LAT, this is the gamma ray survey using the Fermi Observatory. It's a space-based observatory. Now you can see this is the gamma ray sky. You can see gamma ray rich sources, and then the rest of the sky is a lot colder. So likewise, you can also make use of the guided tours in this application, and you can have the guided tours of black holes, supernova. You can make your own tools and send it to the Worldwide Telescope community. Right now, they have this competition called International Worldwide Tool Contest, IWTC. So I'd like to encourage you to take a look at this. I'll share the link on Slack. So you guys can then, if you want, you can make a team of 3-4 and participate in. So this is the International Worldwide Telescope Tool Contest, and that's about it. So it contains catalogs like Prakash mentioned for different sky surveys. So there is SDSS catalog, which is Sloan Digital Sky Survey. Then there are different radio surveys also. So this is done by the Very Large Array project. So this is the radio sky that you see. So it's still taking some time to render. Nevertheless, this is a tool that you can use. I will share both of these tools as well as links on Slack, so you all can access it later on.
Yeah, I've also dropped a link on the chat right now. Aladdin. This is again another tool people quickly use if they want to see. If they're interested in a particular coordinate, you can enter the coordinates here. It will take you to that part of the sky, and you can select any of the given list of different surveys, multi-wavelength, and you can try to see how they look. That particular part of the sky looks in that. So it's probably equivalent, or maybe there's some exclusivity to what information is available here versus the Worldwide Telescope. You can take a closer look depending on your needs. Okay, any other questions? I hope most of you were able to you know work through the worksheets. It's pretty much self-explanatory. In principle, you don't even need a session. You could probably just work through it by reading the instructions over there. If you haven't finished it, please I urge you to go through it during this school or refresher course itself, so that you can get back to us if you have any questions. And for the teachers, especially, please let us know if you are able to implement this uh, for in education for your students. Like to know how it went and if there are ways you think we could improve it. So, are there any other questions? If not, I think we can end this session. And of course, we will still be monitoring the Slack channel and I'll be monitoring the Moodle. So if you have any questions, you can shoot at any time.